Using the clip-on microphone or just the?
I'm going to give folks the option, so
okay.
So I can just turn it off there.
Yeah, so just the on switch, and as soon as this light turns green, it'll be the same on this one. As soon as it turns green, that means it's ready. Okay. Right. Okay. Well, have fun.
Thank you. You look on here. I'll actually do all the computer stuff. I mostly just want you to keep track of time and stuff like that. Do you need any kind of timekeeper?
I can use my phone.
Okay, that'd be perfect. But it
Should I give people like 2-minute warning?
Yeah, and I have a little. Just do a,
Yeah, 2 minutes, and then I'll like stand up.
yeah, and then get close and uncomfortable with them if they're still recalcitrant. I think otherwise.
So the order is different than the order of my preparing.
It is, but it's up there, and these are numbered accordingly. So.
Okay.
But I wanted to sort of just run the technical stuff.
Okay.
Focus on keeping.
Okay, that sounds good.
Okay, hopefully this will work.
Thank you. That opens. I'm happy.
All right.
You're happy? I'm happy.
I'm happy. Yeah.
Awesome. We're happy.
Have you guys signed up for anything for duties?
No, I think we're covered.
Okay.
I may ask you. I may ask you to chair the second session.
Okay. I mean, if you need somebody to sign up, I just want to make sure that.
Let me think about it once we get started. I don't need anything in the first session, so.
Are you checking slides here?
Not anymore. It's almost 2.
Okay.
Can I grab that drive?
Yes, thank you.
You able to find it already?
Yep, you're in.
All right.
I put you in alphabetical order, so I'll let you know when the. You're up after Jesus.
Jesus? Okay, great.
Who actually isn't here yet, so you may be up instead of Jesus.
Too late, but I've got it on here.
Okay. Can you give this to Patchy?
Patchy?
This is for Adam? Or it's
No, it's,
yeah, there's a lot for Adam.
this should be, wait, slide it out so I can see the title. Yes, that's it. It's a large file, it's like 100 megabytes.
I assume that this works because it actually opens. Just look at the slides this way.
Yeah, that's fine. Let's see. Yeah, looks good. Close it here.
Yeah.
Okay, thank you.
Yep.
Thank you. Come right back.
Yank it out. Thank you.
Okay, everyone, thank you very much for attending our cool star Splinter on cool cloudy atmospheres. We have a series of talks in the first session. In the second session, we're going to start with a sparkler session, which Christine tells me is the Australian equivalent of poster pops, which I'm going to use forever now. And then we'll have another series of talks after that, and at the end we'll have a time for folks to ask questions to all the speakers at the end. So the chair for this first session is going to be Carolyn Morley, and I'm going to turn it over to you.
Okay, so our first speaker of this session is going to be Jackie Radigan, and she's going to be telling us about clouds at the LT transition.
Okay.
Push this one over the black. Push it again.
We really ought to make a more like gender clothing neutral version of this.
Yes.
Okay, so thank you to the committee for having me give a review. It's off. Yeah. Okay. So thanks for having me to give a review on what we've learned so far about variability at the LT transition and what this teaches us about the physics of clouds across the LT sequence. So my talk is going to focus on work that's been done mostly from the ground and near-infrared wavelengths on the variability of brown dwarfs. I want to first convince you that brown dwarfs are variable, and this might seem obvious, but if there are people new to the field, I want to convince you that there's now a population of well-documented variable brown dwarfs in the literature, things that are repeatable, reliable detections that we didn't have just 5 years ago. Second, I want to talk about in-depth characterization of these individual targets and tell you what monitoring these targets at different wavelengths has taught us about cloud structure in their atmospheres. And the third thing I want to talk about are population statistics. Is variability more common at certain spectral types? What do the observations say about the frequency of variability at the LT transition? Okay, so just as a brief review of what we think we know observationally about how clouds evolve across the LT sequence. As brown dwarfs cool as they age and they kind of pass the ML boundary at around 2200 Kelvin, silicate clouds condense in their atmosphere. As brown dwarfs cool and become cloudier along the L spectral sequence, they become redder, as indicated in this nice color magnitude diagram by Jacqueline Radigan. And then as they approach around 1200 Kelvin, there's this big color reversal in the color magnitude diagram that signals a shift from really cloudy to clear atmospheres. And so somewhere between late L and mid-T spectral types, clouds are dispersing or dissipating or settling below the photosphere in brown dwarf atmospheres. And then here's kind of the bluer branch of the T-dwarf cooling sequence, which is predominantly, well, what was thought to be predominantly cloud-free, but then I think we're going to hear from Caroline a little later on and Mark about clouds that can form on the T sequence as well. Okay, so one of the big motivators for variability work in the near-infrared has been this idea that perhaps fractional cloud coverage can explain observed properties of this LT transition, the switch between cloudy and clear atmospheres, between late L and mid-T dwarfs. The idea being that if you have a bunch of cloud models with thick clouds, so these lines are all cloud models with thick clouds to thin clouds right to left, and you interpolate between thick cloud models and thin cloud models, you can kind of reproduce this transition. And this is kind of a toy model for how you go from here to here very abruptly. And the key prediction of a model like this is, of course, that we would observe variability specifically in this region where our atmospheres are partially cloudy. Okay, so I want to convince you that this happens and that we see some highly variable brown dwarfs.
Jackie, quick question.
Yeah.
The assumption is that they're variable because they're rotating, right? Not necessarily that you're seeing the changes in real time, but that there's patchiness.
Yeah, in fact, we think we see a combination of both, but we think the structures are coherent enough that, yeah, the time scale of the variability coincides with rotation.
Oh, wow.
So that's right.
Cool.
So there are several well-documented strong variables in the literature right now. The first one was reported in 2009 by Etienne Abhijith, so that's SIMPO 136. It's a T2.5 dwarf with a maximum amplitude of 8%, clearly repeatable high signal-to-noise over multiple epochs. The largest detection we have so far is for a T1.5 dwarf with an amplitude as high as 26%. And this has been well documented over several epochs now, and also by different authors. And then more recently, with the discovery of the Luhman 16 AB system, monitoring for transits of that system actually revealed very strong variability and very fast evolving variability in Luhman 16b, which is a T1 dwarf. So all of these high amplitude detections all happen for early T dwarfs. There are some other examples of brown dwarfs that are reliable variables in the literature outside the LT transition. One is this object 2MASS2228, which is a T6.5 dwarf, which has been observed to vary with HST and Spitzer at a variety of wavelengths. And this isn't in the near infrared, but I just wanted to mention also in this population of well-documented variables, we now have a bunch of radioactive ultra-cool dwarfs that are also known to be variable at optical wavelengths, and this is work done by Leon Harding. And so there's really a reliable population of variable objects now that we can study. Okay, so in terms of these really largely variable objects at the LT transition, this gives us a lot of leverage to do precise measurements of their variability at different wavelengths. And so I want to talk about the things we've learned about cloud structure in these objects based on in-depth characterization. So the first thing is that if you look at variability at different wavelengths, so say K-band and J-band, so this is SIMPO 136, and you can see that it varies more strongly in J than it does in K. If you look at the same plot for 2MASS2139, you see something similar. There was a paper this year of spectroscopic observations of Luhman 16b that showed a similar trend. And so all of these objects have kind of a delta K over delta J variability of 0.5 or so. And what we learned by modeling this are these kind of color variations consistently is that what we think we're looking at is a cool cloud top, so a cool cloudy region, and a thinner cloud region at hotter temperature. So we think the surfaces of these objects are composed of these two types of regions. And all the studies that have tried to model this net number, delta J over K of about 0.5, have come to a similar conclusion that even though you have kind of high clouds and or thick clouds and thin clouds, or high cloud opacity regions and low cloud opacity regions, you don't really have what you would consider a real clearing. You're not looking into regions that are completely cloud-free. And I wanted to kind of illustrate why the models have trouble reproducing that. And so this is a model where you're seeing temperature at the tau of 2/3 surface, or brightness temperature as a function of wavelength for a dust plus gas atmosphere, and then a gas-only atmosphere. And you can see that if you were to poke a hole in the clouds and look down into the deep photosphere, you'd get a huge variation in the J-band. But by the time you get to the K-band, you've got enough molecular opacity there that you're not looking much further down if you remove the clouds. And so if you're just looking into a pure clearing, you expect a huge amplitude in J and a very tiny amplitude in K. And this isn't what we observe. So instead of looking into a pure clearing, we're really looking into a thinner cloud, basically. So we're not looking down as far as we would into a clearing. So I think this kind of summarizes the problem with the clouds and clearings picture. So instead we're looking at variations in cloud thickness across the atmosphere. Okay, so we haven't just taken photometric observations from the ground. We have beautiful high precision spectroscopic time series now with HST WIFC3 of several of these objects. This is an example of one of these time series, and this particular time series is published in the Radigan and Buenzli 2013. And so you can see the variations in the spectra with time. And there are two main points that we, beyond the variations in cloud thickness that I showed on the last slide, that we can take from observations like this. The first is if you take this spectral time series and you decompose it into components, you only need two separate surfaces, or two linear combinations of two separate surfaces to reproduce that entire time series, which is a very simple model. So I can take this realization of surface 1 and surface 2 in different combinations, linear combinations, represented by this line. And this line is a function of phase, and these two surface spectra can reproduce this entire time series. So we're really looking at a basic two-component model of thick clouds and thin clouds. And I don't think we could have hoped the picture to be more simple than this from that standpoint. The second thing that I'll note about the LT transition variables in particular that haven't been true for objects outside the LT transition is that the variability appears to be correlated across a range of wavelengths and pressures. So the variability in the water band is correlated with the variability in the J band and in the H band and in methane. So the amplitudes are different across the spectrum, and this is shown in this plot here. So all of these amplitudes are given relative to the amplitude in the J band, and you see in the continuum you've got high variability, and in the water band the variability is lower. But it's all correlated, and this is presumably governed by some surface distribution of condensates. And gee, I'm running low on time, so I want to end by talking about population statistics. And I know there's been a lot of interest about some different results that have come out lately. Two large surveys have been published, one by myself with 62 L4 to T9 dwarfs, and one by the Brand-Dwarf atmosphere monitoring team with 69 L0 to T9 dwarfs. And the results have differed. So I'm going to skip the explanation of what exactly I did and move to the main result because I'm short on time. But when we plot our detections of variability as a function of spectral type and color, and I've plotted the amplitudes of detections scaling with a linear symbol size, we find all of our strong variables right in the LT transition. We find weak variability elsewhere, but strong J-band variability is concentrated here. And if we do the statistics on this, we exclude the null hypothesis of equal occurrence rates of strong variability inside and outside of this region at 99.7% confidence. So how does this differ with the Brand-Dwarf atmosphere monitoring team? Well, they find strong variability across the entire LT sequence, and they find the rates of variability indistinguishable inside and outside the LT transition. And the methodologies are different, but I think fundamentally the results contradict. And so I wanted to end on a note about reproducibility, and this is based on work that was submitted recently. I've analyzed this data because it's public. It's NTT SOFI data that's in the ESO archive. And for many of these detections, I don't report, I don't recover the same results as the BAM team. So this is 0050, which is like a 9 or 10% detection here. And this is my light curve for it and the light curve of a bunch of reference stars on the chip, and I don't see variability above 0.7% in that particular target. The same thing, oops, same thing for 2225. I do reproduce some of the detections, such as Simple 136, 2139, 2MASS 2228, and this new one here, which is an L6 dwarf, which is actually a spectral standard. Okay. So the summary of that is that I reproduce 4 of 13 claimed strong detections of variability from the BAM sample. 3 of those are well-documented variables in the literature. One is this new L6 detection. I put limits on the remaining targets of 0.7 to 1.6% in variability. If you combine the revised BAM sample based on their reported null detections, based on my found null detections, and the variability that is found, you see we're still finding a higher incidence of variability inside the LT transition just based on that revised BAM sample. If you combine it with the Radigan 14 sample, again, we're finding similar results. About 22% observed occurrence rate of variability in the LT transition, about 3% outside. Using binomial statistics, this excludes the null hypothesis at about 98%. And so I think observations to date are still favoring an increase in the frequency of large variability, at least around 1 micron wavelengths inside the LT transition, and I will finish there.
We have time for 1 or 2 questions for Jackie.
So I was wondering how the model explains. So you have your model of. How the fractional cloud coverage changes over the LT transition. How does this explain the variables you found that are like L4 and the T6.5 object?
I wouldn't say it's so much of a model as a hypothesis that overall LT atmospheres are expected to be patchier or more heterogeneous than objects outside. So I think it's really interesting to try to understand what's going on with these other objects. And I think the way to go about this is to get multi-wavelength observations of all of these objects and try to understand if there are trends, and we can understand the different physics involved at different spectral types.
Okay, there are no more questions. Oh, there's one in the back. Derek?
Yeah, where would you see the main problem with using variable if you adjust, for example, the communication?
I would be speculating. Our procedures are very different. So one thing I'm going to do is make my code public, though, which I forgot to mention. So I'm going to put that on my website, and it's a pipeline. It's pretty user-friendly. You can download it. It's point and click. You can play around with the different parameters. And so shortly after Cool Stars, I hope to get that on my website, and people can play with it. What's that?
You have a cloud code in there as well?
In my code? Or
talking about the atmosphere models, right?
Oh, sorry.
You said they didn't seem to be able to.
Sorry, I misunderstood your question. I thought you were talking about the data issue.
Is it because the clouds are just sinking deeper into the atmosphere instead of?
I'm not sure I've understood your question.
Well, maybe I didn't understand that.
I mean, are you asking why the models aren't reproducing?
Well, you said that
there seemed to be a problem, I think, with the K-band. I think the long wavelength amplitudes compared to the J amplitudes are higher than you would expect for a model with clouds and clearings. The solution to that is that you're not looking at clouds and clearings. You're looking at scale height variations of clouds across.
So why don't we take this?
So we can discuss after.
And let's thank Jackie again, please. Still attached to you. Still attached. Okay.
No, the other one.
Okay, our next speaker is going to be Rajan, who's going to be talking about his variability survey.
All right. I'd like to thank the organizers for including me in today's Splinter session. My name is Abhijith Rajan, and I am a PhD student at the Arizona State University. I'm here to talk about the Brown Dwarf Atmosphere Monitoring Project, or BAM, as we like to call it. It forms a part of my thesis, and so let me get started. All right, so we conducted a uniform study monitoring 69 L0 to T8 brown dwarfs. So it's published in ANA recently. And the histogram shows how we covered the entire LT sequence with equal number of brown dwarfs in the early L transition and late T. For the survey, all the objects were monitored at the NTT. The survey was conducted over 2 weeks. And to maximize the efficiency of the observing program, we observed 2 objects in pairs with approximately 3 hours duration per object. So the survey detected 14 variables, including 9 new and confirmed 5, irrespective of what was just said. The figure shows a similar histogram as what was shown earlier, and the table indicates the frequency of variability seen in each of these bins. And we find no statistical significance in any of the bins, and the transition was defined by using the Galmowski et al. 2004 LT transition. And even if we adjusted the boundaries, we didn't actually see a different result in the statistical significance. However, I will take a minute to talk about the similarities between Jackie's survey and ours. We actually monitored about half our sample, which had the same objects. And these solid lines indicate the same result, and the dashed lines indicate opposite, either classified as variable or constant. And 90% of the targets were actually classified similarly. The right two panels actually, according to me, show the big difference between our surveys. We monitored the entire L and T range, and as you can see, there's a greater number of LT transition and late T objects in Jackie's survey. So the Radigan et al. Study concluded that high amplitude variability is focused in the LT transition, and the BAM1 results, despite the numbers, actually show that there are existing high amplitude variables in the early Ls and in the late T. And this has actually been confirmed by Jackie in her reproduction of our data. So I think it's actually a very interesting set of objects that have now been observed and are ready for follow-up studies. And in fact, I'm just showing the figure that Jackie showed earlier. This is an amplitude versus spectral type. Our study shows no spectral amplitude dependence on the spectrum, but it does have a large number of variables that have been detected. And in fact, all of these variables are currently being followed up as part of our BAM3 study with the ESO NTT telescope. And I would like to quickly show you some of our follow-up data. In fact, here's 1010 in the detection epoch in the paper with a Nordic optical telescope follow-up study. Similarly, here's 2228 showing a nice large amplitude variation. We've got J and H band on 2M1300, and it shows clear variations. Similarly, 1126 shows greater than 2% variations, and in fact, all our observations are multi-wavelength, multi-epoch, so that we can come back to the same object within the same program and see if the variations continue. Similarly, by having multi-wavelength studies, we can actually start to try and analyze these objects over the different wavelengths simultaneously. Another area of investigation for the BAM1 project was the question of persistence of variability. And by combining our results with literature results, we were able to just get a preliminary idea of whether these objects vary consistently or not. And actually, the interesting result to us was that nearly 40% of previously monitored BAM1 targets actually switched states. So you have 13 objects, which is 40% of our BAM1 objects, changing from between variable and constant. And this indicates that multi-epoch observations are actually invaluable in properly characterizing brown dwarf atmospheres. And our BAM2 study actually pursues the question of persistence and evolution of brown dwarf variability. It's a pilot study. We've only got 4 late T and Y dwarfs, including 4 epochs on the planetary mass object ROS 458, all 4 which showed us flat lines, unfortunately. So 3 of the 4 objects are constant in all observations. However, we've got YSO 458. It's a remarkable system. It's a binary star. It's a binary brown dwarf system, and it shows this large 17% amplitude variation in one epoch. We come back to it 2 years later, and this variability is no longer visible. Now, the question is, what exactly is going on? And we don't really know. But we do want to follow this up over and over again. Now, finally, if you combine our BAM2 results with the BAM1 and literature, we were actually able to explore variability over multiple epochs. The circles are variables, the triangles are limits, the dashes indicate objects that switch, and the solid lines indicate objects that stay constant, consistent. So variables stay variable, constant stay constant. 13 objects switch states, including Y0458, but even the objects that have been measured to be variable by the same people actually never show the same persistent amplitude in different epochs, which we think is really, really fascinating. And if you plot these objects, the coolest of the objects in this red box over here, these are all the T5 and Y0 objects. If you plot them on a color plot, we used the Sama et al. And Morley et al. Models, we're actually starting to see possibly a trend in these brown dwarfs. What we're seeing is that if you plot the constants, which are the red objects, and the variables, which are the blue objects, along with these white dwarf purple objects, we're actually starting to see that the constants are concentrated at the clear atmosphere. So they are the bluest objects in the study, whereas the variables, aside from this one guy, seem to all have redder colors. Unfortunately, Y1738, even though it's part of our study, had a rather poor upper limit. And so we can't really state anything about whether it shows variability at anything less than 10%. So that's the only reason why it's not being shown as a variable. However, all of these targets, if this is true, then all of these targets are really, really interesting white dwarfs that are potentially could be variable. And finally, conclusion, we have monitored 73 brown dwarfs from all over the entire L0 to Y0 spectral range. And we found high amplitude variables outside the transition, which we think is really, really valuable because we have an L3, an L6, an L5, a T6 that have been confirmed to show variations across multiple epochs. And our Biome 3 follow-up is a multi-epoch, multi-wavelength study. Thank you.
We have time for 1 or 2 questions for Abhi.
I'm curious, the objects show variability and then in one epoch, and then don't show variability in so the objects that show variability in one epoch and then don't show variability in the other epoch. Just a very fast question. Did you guys use the same reference star for both?
For the BAM study, yes, but a lot of the results that we have is actually using just literature results. So in those cases, we've just taken whatever is the published result.
So you compared the published result before to what you observe now, and you don't see the variability, or you do?
Yes, exactly the same objects.
So you're using the same exact reference star?
Yeah.
Okay.
Jackie?
Yes, I wanted to ask about reference stars. Because I noticed you showed all of your light curves, but there are no reference star comparisons. And so I think this is just kind of an important thing to check, that not only your master reference, which I think is your average of all of your reference stars, but just individual stars of similar brightness to your target, should show less variation than your target. So I was wondering if that's something that you've looked at.
We do, and actually, in most cases, that is the case. The way our pipeline works also is that we tend to choose the objects with the flattest lines in our field. So, yes, our references are pretty flat, almost all our cases.
Okay, thanks.
Let's thank Abhi again.
Okay, our next speaker is going to be Stan Metchev, telling us about his Spitzer survey.
Good afternoon. You've probably noticed that there's a little bit of a controversy here. Whether brown dwarfs are variable at all spectral subtypes or just at the LT transition, and what the amplitudes are. I'm going to drip a little bit of extra oil into that fire. Now, all these results are ground-based so far, and the ground-based work is pioneering. It's very important. It's really the only way to do very large studies. I'm here to tell you that the truth resides in space. and that's a serious statement. The reason is that we can get much higher precision, much longer cadence, much longer durations of observations, and much higher cadences. And so this allows us to ultimately detect much lower amplitude variables. So the blanket statement on my title slide is the conclusion of the talk. So you don't have to stay for it if you don't want to. I've put it down, however, as an indication of the kinds of possibilities now we have open in front of us. With every single brown dwarf being spotted, we really have a very powerful tool at our hands to study these atmospheres in depth. And there'll be more about this kind of work in later talks today and tomorrow. Also, all brown dwarfs, or at least half of them, are observed to be variable. I will add, however, that the amplitudes which are observed tend to be very small. And this is, again, a direct result of the precision that we can attain with space-based observations. So I'm talking about the observations from space, and I cannot do this without mentioning the very first work that actually attempted this. This was a paper by Maria Morales Calderon and co-authors, a 2006 paper which studied 3 late L dwarfs in an attempt to look for variability in their light curves. And the precision is just astounding. The data points have 3 millimagnitude error bars. The amplitudes they detect in these 2 objects are about 10 millimagnitudes, so 1%. 1%. Now, the authors were very careful about concluding anything from these data sets. This was the early days of precision photometry and faint objects with Spitzer, and there were a number of caveats that they very carefully pointed out. There's ambiguity in the light curves that remains after correcting for the pixel phase effect in Spitzer observations. This is a consequence of where your star falls exactly on a pixel in Spitzer. There is issues with the periodic movement of Spitzer's Bohr side pointing. And also, they only detected variability in one of the bands, but not in the other. So this lack of confirmation was troubling for them. And also, the periods that they actually inferred were longer than the duration of the AOR. So again, this is another warning sign that what you're observing may be questionable. Nonetheless, knowing what we know nowadays, I would say that both of these objects, in fact, are bona fide detections of variables. And this work pointed out 2 important ways to approach this problem. Very high cadence, staring observations over long duration. This is how you're going to get bona fide detections of your low amplitude variables. Now, that said, a recent survey with HST actually employed very short durations, a single HST orbit, 40 minutes, but again at very high precision. And this was using the GRISM spectrograph on the HST WESC3 slitless GRISM spectroscopy. And they did a snapshot survey. In the end, they got 22 targets in the spectral range L5 to 8 T6, found 5 high confidence variables. And their results basically suggest that these variables, the high confidence ones, can be found more or less scattered throughout the mid-L to mid-T dwarfs. And there were some lower confidence variables shown in the blue symbols, and they more or less follow the same distribution as well. A number of interesting things come out of result spectroscopic observations. The first important thing that came out of that result was that often the variability is limited to very narrow wavelength ranges that you actually smear over if you look at broadband. So broadband observations are less likely to detect this variability unless you have narrowband filters. Also, the slopes tend to be very small. So again, this hints at very small amplitude variability. But importantly now, because you can trace where the variability happens, you can actually look for the dominant species that are being suppressed and say something about the composition of the cloud condensates that are actually suppressing the emission at these particular wavelengths. So you're really starting to probe in depth in the atmosphere with time-resolved spectroscopic observations. A very interesting result that's featured in the poster by Hao Yang at this conference is one that compares the variations in L dwarfs versus T dwarfs, like one L dwarf compared to one T dwarf, and the blue and the red curves here show the spectrum at minimum and maximum light, and the bottom panels show the ratios. And you can see in the L dwarf you don't see any change in the variability. You don't see much of a change in the variability over the 1 to 1.7 micron range, but in the T-dwarfs, you see decreased variability amplitude in the water band. And they interpret this as the fact that the clouds that are actually causing the variability are way below the water column, so you don't see much of an effect in the end on the strength of the water absorption in the variable. Another very neat result from this survey is simultaneous observation of one object. To my understanding, this is the only object for which so far we have simultaneous HST and Spitzer observations. You can see the HST epochs on top and the Spitzer 6-hour epoch on the bottom. And the very interesting thing that came out of this, you can actually find phase shifts in the light curve as a function of wavelength. And that's what's plotted here. This is the phase shift in degrees, and you can see as a function of pressure, this actually points to some picture where you have a delay in the variability at high altitudes. So there's some driving that's happening at potentially at low altitudes and deeper in the atmosphere, and it's getting delayed when it goes up. So this was actually an idea that was proposed by Tyler and Robinson. Tyler Robinson is the first author. Robinson and Marley is the actual paper. My apologies. They're both over there. Apologies. And this will be further shown in Esther Buenzli's and Daniela Pai's talks today and tomorrow. Now, continuing on to the pursuit of the truth, now we'll switch bands a little bit, go from HST to Spitzer. A couple of years ago, we started and now finished a Spitzer exploration science program to look for variability across a broad range of spectral types in the brown dwarfs, L3 to T8. And what we did is we really actually extended the lesson that was learned from the Morales-Calderon survey. We actually, instead of doing 6.5-hour observations of a single object, we actually asked for 21 hours per object. And I should say this was not possible at the time the Morales-Calderon observations were taken, because this was during cryogenic observations, and only since then has the observation mode of Spitzer allowed us to do these longer observations. So we actually have 21 hours per target in continuous monitoring shared between the two bands in the warm Spitzer. And the advantage, obviously, is the much higher precision over ground-based observations. And the way we really approach this is we have Jupiter as a nice model of spotted a giant planet in the solar system. We wanted to see to what extent this is actually representative of all the other substellar objects in the galaxy. So really the goal was to detect great red spot analogs on brown dwarfs. The results that we have from this is that we found 20 variables among our 43 targets, so 47% of objects were variable. They're not exactly uniformly spread as a function of spectral type. The L dwarfs seem more commonly variable. 2/3 of them are variable than the T dwarfs. Only 1/3 of them are variable. The interesting thing, though, is that if you look at our the distribution of our sample as a function of magnitude, the L dwarfs just happen to be brighter. So it's actually easier to detect low amplitude variability around the L dwarfs. And if we limit ourselves only to objects that are brighter than 12th magnitude, we see that fully 85% of them are actually variable. What we're finding is that most of the amplitudes are smaller than 1%, and we can find amplitudes as small as 0.2%. The periods that we find, again, one has to be careful with ground-based observations. The diurnal cycle complicates interpretation of data quite a bit. We're actually finding trends that are as long as the duration of our observation. So we cannot claim a period of 20 hours at this point because our duration of observation is 20 hours. But I would caution very strongly against interpreting periods that are within the limit of your observation, as has often been the case with ground-based studies, or even over a single night. Given this sort of trend well, you can see our sensitivity limits over here as a function of magnitude. So this space we just can't explore. We're not sensitive enough with our observations. But there is not much of a reason to expect that there's no low amplitude variability more or less throughout the LNT sequence. So we can do some sort of moderate completeness correction and assume we have some sort of uniform amplitude distribution. This would not be entirely unfounded. For example, if we look at the other band on which we observed 4.5 microns, not the 3.6 micron data which are shown here in these data points, you can see we have a low amplitude variable at 4.5 microns, and it's a T dwarf. So we have good reason to expect that we might actually have low amplitude T variables. So that's what we find. spectral type versus color. We see lots of variables in the L's, and then circles denoting here areas of the area of the circle denoting the amplitude of the variability. We see a gradual trend for increasing maximum amplitude and variability. And this is our incompleteness correction here, 50% of T dwarfs, 80% of L dwarfs or so being variable. And I should point out there's a poster by Kevin Carlisle which shows that the variability in fact extends into the white dwarfs as well. Now going into this, we had a very cutesy way of estimating what fraction of our objects should be variable. We said, well, let's look at Jupiter where the spots are, they're within plus or minus 45 degrees. If we just assume a random orientation of spin axes and a binary outcome detection or not, we'd actually expect detection in about 50% of cases. So this agrees with what we're finding for the T dwarfs, but then the L dwarfs are much more keen in terms of variability than that. So what we're concluding, in fact, is that all T dwarfs have at least one spot, but L dwarfs most likely have multiple spots. So these are two of the key results that I'm sharing with you from our program. All of the L and T dwarfs that we observed have at least one spot, but the L dwarfs have multiples. One important result that I wanted to point out as well is the L dwarfs are very interesting. Because we have higher precision observations, we can learn a lot more about them. So the first result that we published was on this nice single mode variable, an early L dwarf. We found the amplitude, we observed the variability in 3.6 microns, nothing in 4.5. The conclusion in this paper by Ari Heinz et al. Was that there was a hot spot in the cooler atmosphere. We favored clouds. We could not completely exclude magnetic activity. That's still to be decided. But if we look at some of the other L dwarfs, they show much more complex light curves. So there's a poster by Ari Heinz at this conference. So we see often irregular variables among the L's, and what Ari terms as wild weather. So we see rapid changes in the spottedness of the objects. So this is my summary. Spots are ubiquitous, as I told in the title slide. Two important sets of results. Spitzer says that everything has at least one spot, all brown dwarfs, and the L dwarfs have multiple spots and are often rapidly changing. The HST slit spectroscopy has opened a treasure trove of what we can learn about these atmospheres. We see wave-independent phase shifts and differential absorption strengths. So we actually can really probe these atmospheres in depth now for real. And the important thing is the precision and the cadence of the space-based observations is absolutely essential to infer any of these results. Thank you.
Okay, we have time for questions. Let's start with Trent.
Okay, so I'm a neutral party in this conference.
There's three parties.
I have a question about your sort of overall thing about looking for truth and everything. So HST is in space, but it's also tied to sort of a diurnal cycle. It's actually kind of worse from the ground because you only get 45 minutes to an hour or something on each observation. So how much of it is the problem with the ground-based, the short cadence or the short observing window, and how much of it is other factors that are something outside of space?
So part of the answer is that the periods that we observe tend to be longer than about 2 HST orbits anyway. So HST actually can sample them more or less well. The problem with HST is you rarely get more than one orbit per object, so you usually just see a trend. The issue with the diurnal cycle from the ground is more than just day and night. You have changes in air mass, which are actually very crucial, and differential water absorption. So there's more complications just a simple diurnal cycle from the Earth.
Hi, Katerina Oliveira from European Space Agency. I was wondering, because you were showing light curves mostly in the mid-infrared, and before we're seeing near-infrared, and also different kind of periods of coverage. But could you be also looking at different phenomena, because you are assuming that your spot is not changing, and maybe from the ground they could be monitoring changes in the spot itself, no? I don't know, it's a question.
That's a very good question and a good observation. The ground-based data have already shown that these spots will change over time, and we also are probing different levels in the atmosphere. That's already toward the way of resolving this controversy that there is currently.
Okay, one more question.
Let me ask a somewhat related question. Are the models good enough for you to say whether you're, John Stauffer from IBEC, are the models good enough to say whether your observations are contradictory to what's seen from the ground in terms of amplitudes.
I would really have to defer this to Carolyn and Mark. I would probably say something stupid if I try to answer this from the podium. But there'll be a talk later by Carolyn Morley, so hopefully she'll answer that.
Okay, let's thank Stan again, please. Okay, next we're going to hear from Adam Showman.
Hello. So hopefully you're already convinced that there's weather and interesting dynamics on brown dwarfs. Just to summarize, even the sheer existence of clouds imply vertical mixing is necessary to keep the cloud particles lofted. So there's been evidence for that for a couple decades. Disequilibrium chemistry as well. Methane and CO are quenched out of equilibrium commonly, as is NH3 with respect to N2, also indicating vertical mixing and necessary to cause the quenching. We've seen a lot about light curve variability already, and just showing the first bit of the example that Jackie showed from this pioneering paper by Artigau. And then also Ian Crossfield recently had a paper doing Doppler imaging for one of the Luhman brown dwarfs, Luhman 16b, and showed surface patchiness, probably due to clouds. And so given all this evidence, it's interesting to try to understand what the dynamical regime is, learn about the dynamics of these bodies, and eventually try to link back to and understand the observations. Brown dwarfs are rapidly rotating with typical periods of 2 to 12 hours, so faster than Jupiter. And this implies, for any plausible wind speed, a rotational domination of the dynamics at large scales. In other words, the Rossby number is going to be much less than 1. This implies in the horizontal momentum equation that there'll be a force balance between Coriolis forces and pressure gradient forces. The Earth at large scales, as well as all the giant planets in our own solar system, are also in this regime. So it's actually quite sophisticated understanding of how that regime works, built up over the last 50 years in the solar system literature. Also, brown dwarfs, of course, have a vigorously convecting interior necessary to get rid of their enormous, or transport their enormous heat fluxes. Yet, of course, their atmospheres will become stably stratified with a transition at typically a bar or so. And what's interesting, as far as a contrast with solar system atmospheres or radiated atmospheres in general, comparing to, say, Earth or a hot Jupiter, is that there's no external gradient in irradiation. The main mechanism for driving an atmospheric circulation on the Earth or on a hot Jupiter is the contrast in stellar heating and absorption of stellar energy from, say, the day side to the night side or equator to pole. That's absent on a typical brown dwarf. Instead, you have convection from below, modeled very nicely in a local box model by Freytag et al. 2010. The convection from below then impinges on the radioconvective boundary and triggers a wide class of wave modes. This was a 2D study neglecting rotation, and so they were only able to resolve gravity or buoyancy modes, but on a 3D object at large scales, you also expect Rossby modes and coupled Rossby and gravity modes, which are, and Rossby modes, I might add, they're sort of vorticity type waves that result from the gradient in planetary rotation strength with latitude, and they're the most important class of wave mode in the atmosphere of Earth and Jupiter, for example. They're the dominant wave mode of driving large-scale circulation. Okay, so this provides some sort of sense of the regime we're in, and so the key difference then in the circulation regime is that this convection will drive these modes, and the question then is to what extent will those waves interact with each other or cause turbulence that leads to storms, vortices like the Great Red Spot, zonal jets, and so on. Okay, so motivation then, what is the atmospheric circulation like on brown dwarfs? Are there zonal jets? By this I mean east-west jet streams in the atmosphere analogous to the jet streams in Earth's atmosphere. I'm not talking about jets spraying stuff out of space here. Large vortices like the Great Red Spot or the hundreds of other vortices on Jupiter and Saturn, fluctuating turbulence, what are the wind speeds, temperature fluctuations, and key length scales, how does this depend on the internal flux, spectral type, and so on. What controls the relative importance and amplitudes of zonal jets versus vortices versus active storms in the atmosphere? Are there regimes under which one dominates over the other? That's sort of a fundamental question in planetary atmospheric fluid dynamics. Also, it's interesting to understand how the turbulence depends on latitude. Is it similar everywhere over the globe, or is there a strong latitude dependence, and if so, why? And then also to try to understand implications for cloud patchiness, light curves, and so on. So I'll mention that with my group, we're starting sort of a systematic sequence of studies to understand this. And so Zhang, a postdoc at the University of Arizona working with me, will give a talk following mine. And then Shenyu Tan is one of my graduate students here on the aisle. He's got a poster. And we're basically trying to start with very idealized models to try to understand how the planetary rotation interacts with the turbulence to produce large-scale coherent structures under regimes relevant to brown dwarfs. So we're starting very idealized, without clouds, and forced in a very simple manner. And the idea is to very systematically and slowly sort of build up complexity so we can understand what the mechanisms are doing in a step-by-step fashion. So it may take a couple of years before we're quite ready to sort of meet the observations headway as far as light curve predictions and so on. But we're doing our best. Okay, so the goal in this study that I'm going to talk about is I want to understand what sort of 3D atmospheric circulation results from convective forcing at the radioconvective boundary. So you imagine the convection from below, the plumes sort of, whoops, what just happened? Thank you. Okay, so the convection comes up from below, and that interacts with the stably stratified atmosphere, and we want to understand what happens in that atmosphere. And doing calculations of the 3D convection with the convective scales well resolved, also including a stratified atmosphere, is a challenge. And also, there's strong dependences on the numerical parameters as far as what kind of convective length scales you get and so on. And so the approach that I've used instead of doing that is to parameterize the convection at the bottom of the model. And put in turbulent forcing at the bottom, so shown schematically here versus longitude and latitude. The idea is this represents the perturbations caused by all the convective plumes. And this is constructed in a way to be isotropic, so there's no directionality associated with this pattern. There's no distinction between east-west and north-south. And it's also homogeneous over the sphere. There's no statistical difference between how the forcing is introduced at the equator versus the poles. And in this particular runs that I'll show here, the characteristic wave number is 20. This is a free parameter that will be varying. The radiative cooling to space is parameterized in a very simple manner. Rather than using radiative transfer, we use a so-called Newtonian cooling scheme. So we have a defined radiative equilibrium temperature, TE, which is a function of pressure, and we simply relax the local temperature, which is a function of longitude, latitude, pressure, and time, toward that radiative equilibrium over a characteristic radiative time constant. So the radiative time constant is specified as a free parameter in this study, and then TE is a function of pressure. It's shown here, and again, could be viewed as a free parameter, but it's taken to mimic brown dwarf models, going from an 80 baud at the bottom up to something that approaches sort of quasi-isothermal at the top. All the little squares are showing the vertical levels in our 3D model to give you a sense of the resolution here. And these convective perturbations are stuck in at the bottom here, from 10 to about, say, 3 bars. The radioconvective boundary is just above that. The typical range of photospheric pressures at various infrared wavelengths is shown here. So the convective forcing is occurring at the bottom and is triggering turbulence and dynamics in the region where radiation will happen to space. And so I'm systematically going to vary the radiative time constant and see how this affects the dynamics. I'm going to show a sequence of results, movies, which the left panel will show a color scheme. That's showing the east-west wind speed over time in the simulation. The right panel is an orange scale. We'll show the temperature, all at a pressure of about 1 bar, which is similar to the photospheric pressure at a typical infrared wavelength. I'll just make a little apology and warning. The movies themselves are fine, but there's some problem with rendering on the PowerPoint. And so you're going to see the left-hand frame jitter sometimes and produce weird, flashy, black and white kind of contours. So try not to be distracted by that. That's not what the actual atmosphere is doing. And so hopefully, don't focus too much on that and just try to pay attention to the dynamics. Okay, so let's see. This one needs to be, where's right here? Okay, there we go. Okay, so this is with a radiative time constant of 10 to the 4 seconds. And so You can see the flash there. And so despite the fact that the convection turbulent forcing is isotropic and covers the full globe, the main activity is actually occurring near the equator. There's lots and lots of waves. There's turbulence occurring all over the poles at very low amplitude. You can see that in the plot of the east-west wind speed here, these sort of turbulent structures. And you see these kind of zonally banded pattern, but only near the equator. It's confined very close to the equator. Outside that, you just see kind of quasi-isotropic turbulence. This is a very short radiative time constant, maybe corresponding to a temperature of 1500 to 2000 Kelvin. And the effect that this is having, the turbulence from below, leads to wave propagation upward. The vertical motion from that is causing entropy variations, entropy advection upward and downward, and so that's producing horizontal temperature variations on an isobar. And radiation is relaxing those away. So in the context of this model, radiation is a damper. It's removing energy from the system. And it's doing so very, very strongly here. And it's preventing the existence of zonal jets here because it's damping the turbulent energy faster than the energy can reorganize into east-west bands. Okay, so let's see if we can move. Okay, so this is at 10 to the 5 seconds. These are not quite starting automatically here, but let's see if we can get this to start. Okay, yeah, so 10 to the 5 seconds, which is still rather short. You can see there's still a confinement toward the equator, but there's starting to be more activity at the poles, and you can see that there is a pattern, a systematic pattern of east-west flow, even at the higher latitudes. And the east-west wind pattern here, you can see that red is eastward wind, blue is westward, and so you can see we're starting to produce a nice banded pattern, qualitatively similar to Jupiter, going up to maybe 45 degrees. The radiative time constant on Jupiter is more like something like 10 to the 9 seconds. So it's interesting to see this pattern, even at such a short radiative time constant. Okay, I'm going to run out of time here. I can see these movies are going a little slow. Okay, so 10 to the 6 seconds. And so still we have kind of a activity near the equator, but it's also extending up with vortex-type structures. The higher latitudes, the jet pattern is extending essentially now all the way from pole to pole. Even shows polygons around the northern hemisphere, similar to those, for instance, to the polar hexagon observed on Saturn. And then finally to 10 to the 7 seconds, and now we'd be here at temperatures. We're going to move forward to. Okay. Okay, so here finally it's fairly global. The equator is still has shorter time scales, but the jet pattern is still going all the way to the poles. Just to give you a sense of what the pattern in that last model looks like over time in a rectangular projection. So you can see the rather rapid activity at the equator, but still there's systematic jets going all the way up to the poles that you can see here, with a significant amount of shear and turbulence going on. If you look at the east-west wind speed averaged in longitude, this is shown here for these 4 models as a function of latitude on the x-axis, the equator at the middle, and North Pole on the right, South Pole on the left, versus pressure. So this is sort of the height coordinate here. So the structures you can see confined toward the equator in the 10 to the 4 second radiative time constant case, and the expansion out to the being global. You can also get a sense of the wind speeds, which are rather weak when the damping is strong and get out to hundreds of meters a second. I do not have time to discuss why the equatorial regions are most active, but we have a little theory of this. I'll just mention that the turbulence that you're seeing is associated with vertical motion pattern, and even though these models themselves don't have clouds, once we include cloud cycles, this will automatically lead to cloud patchiness, because the vertical motions associated with this turbulence will bring up material that can condense and produce clouds in some regions, and there'll be absence of those strong clouds in others. So I'll just stop there. Thank you.
We have time for a couple of questions for Adam. Yeah, in the back.
Hey, John, how are you?
Good, thanks. So, of course, I guess the bands will sort of average out, like in most sort of photometric variability studies, I imagine. Do you have a way to predict, like, great red spots or dark ovals or other sorts of structure that will show up very strongly in sort of the photometric? Or is that,
Well, there's a lot of eddies that exist even on the jets, which you can see quite well, for example, in that last rectangular projection movie that I showed. So yes, there are jets, but there are, sort of, eddies that have temperature perturbations on an isobar of 5 or 10 Kelvin, and there's vertical motion fields, I think, will produce longitude variations in the cloud structure, even when the jets are kind of the dominant structures. But yeah, we have to obviously put clouds in the model to quantify that better.
Okay, just to follow up, is that jet structure putting kind of an upper limit on the typical feature sizes that you would expect to cause variability?
We need to explore the parameter space better. So I showed here the dependence on the radiative time constant. We also need to systematically vary the length, the wave number of the convective forcing, and the amplitude of the forcing, and the time scales. So, but yeah, I mean, I would expect, generally speaking, there's probably a sort of a Rhine scaling holds here, where in cases with hundreds of meters per second wind speed or up jets, they're sort of 10 to the 4 kilometers wide or something. The rotation rate I should mention in those models is 5 hours.
We have one more question for us?
I have a question.
Okay.
Kind of in terms of the temperature contrast that you get from the model, I've seen something like 30, 40 kelvins. Can you make larger temperature differences? What parameters set that, and what would be the maximum?
That's going to be hard. The forcing here, I think, is already toward the strong end of what's realistic. But again, when observers such as yourselves are talking about flux variations, what you're really talking about is brightness temperature variations. And so the key point is that all the temperature variations are being shown here are actual temperature variations on an isobar, like on a constant height surface, roughly. And so a few Kelvin horizontal temperature variation on an isobar can easily be associated with modulation of the vertical wind pattern, and therefore cause cloudy regions in some places and more cloud-free regions in other places, and that can have a brightness temperature variation of hundreds of Kelvin. So those are completely different issues.
Okay, let's thank Adam again. So our next speaker is going to be Zhang, who's going to be telling us about atmospheric circulation.
So, good afternoon, everybody. I'm Xi from University of Arizona. So I'm working with Adam Showman. Today I'm going to talk about our recent FJ letter paper on the atmospheric circulation on brown dwarfs. We specifically focus on formation of jets, vortices, turbulences, eddies, and what kind of implications of our model on the recently observed time variability of the light curves. And here, if you Google brown dwarfs, you can see some beautiful artistic images, and from hotter dwarfs to cold Jupiters. And some people just kind of see bad features, belt zones and something like Jupiter in the cold dwarfs, and you can see multiple cells and isotropic features in the hotter ones. Is that true? It's not. We're interested in that. So since time is limited, I just quickly summarize my results here. Take home message 1 is we find 2 control key parameters that are governing this formation of jets on brown dwarf atmospheres. The first one is internal heat flux, and the second one is radiative damping. So of course, the internal heat flux here means a lot of things. It means like convective interior, what kind of activities of the convective flux, what kind of moist convection activities for clouds, and for the radiative damping, we just folded everything there, including cloud opacities, temperatures, everything there. But we just want to bring everything down to the basic physics here. We found the forcing to the system and the damping of the system. If the damping is weak compared with the forcing is high, damping is weak, we sort of get body structures and get jets, as Adam just showed in 3D models. If the radiative damping is high or strong, and the heat flux, the forcing is not strong enough, you turn to have isotropic turbulence or eddies dominant, and we see the multiple cells on the sphere of the brown dwarfs. So, and the second take-home message is our simulated light curves capture the important features of recent infrared observations, such as the amplitude variation of a few percent and multiple peak shapes. And we can see the light curves change with time from our simulations. So this is our paper. Okay, quickly, this model setup. This is actually a 2D model. It's even simpler than what Adam showed. And we focus on stratified layer overlying the convective interior. And this is a 2D global shallow water model, just calculates about one single layer thickness. And we use global spectral forcing because people studying interior models tells us we have a fully convective system for brown dwarfs. and we have a simple linear relaxation scheme for radiative cooling. So this is very simple, but we have some advantage of this this kind of model. First, it's simple, okay, but it captures the essential physics. So that we call the shallow water model is a minimum recipe for simulating the brown dwarf atmospheres. And the simulation is quick, so we can do a lot of runs, and we can search the parameter space and do some statistics and see what's going on. And we can do long-term integration, so we can see what light curves evolves with time. So here I just show some, samples. Here is a jet case, which we put like strong forcing and weak damping. Initially, you have like isotropic turbulence, but it quickly generate jets, produce jets at the equator. Here is the layer thickness pattern. Here is a zonal mean, zonal wind. And if you have like less forcing and you have strong damping, it turns out like isotropic turbulences. Because the perturbation is quickly damped by the strong damping, so we don't have like a jet pattern or bandit pattern seen from here. And we can do statistics, as I said. This is a relaxation time scale, and here's the energy input to the system. If you have strong energy input and you have weaker damping, means the time scale is longer. You sort of have like Jupiter pattern here. This orange dots means we observed jets in our simulations, and those blue dots means we didn't observe any jets. And if you have like less energy input to the system and you have strong relaxation time scale, like 10 to the 5 or 10 to the 4, depends on the specific situation of the brown dwarf. You either have like a isotropic turbulence eddies situation, or you have jet patterns. And okay, here are a lot of like beautiful data and fantastic jobs done by various groups here, and I cannot list all of them. But what those data tells us is the light curve changes with time, and light curve changes with wavelengths. And can we simulate that from our observation, from our models? Yes, we do. So here I show a movie here. We use a proxy of the layer thickness and integrate it over the disk and look at it as a brown dwarf rotates. So this is again the 2D map, latitude, longitude, layer thickness, and here I integrate it as it evolves. You can see two features. First, we have the light curves, and second one, the light curve changes. Both the shape of the light curves and the amplitude of the light curves changes with time. So this simple model does capture some interesting features here. And if we look at it more carefully here, so here is some snapshots from the long-term integration. Okay, this is several years, and we did two cases. This case is with jets. This case is strong damping, means like hot brown dwarfs. And take some snapshots. You can see the light curve changes, both in shape and amplitude. So that's not surprising to us. If you guys observe the light curve changes as function time. And if you do Fourier transform for this time series, you can see these features are actually dominated by rotation modes, several rotation modes and multiple modes of the rotation. So that's very interesting. And one thing I didn't put in paper, but I want to mention it here, is can we understand the amplitude of the light curve variability? So as Peter just said, from the speaker, we just observed a lot of data showing the amplitude of the light curve is less, the variability is less than 1%. And sometimes we see large variations. So why is that? If we look at this 2D maps, here you can consider this local maximum to minimum changes is like order unity, or like 30% or something like that. People actually have done that, using like a cloud model, and to look at the local temperature perturbations. If we have like a 50% changes or amplitude changes of the local patches, and if you look at this, how many patches here is roughly like 100, and this is nothing more like the statistics of the noise compared with the integrated signal. So it's squared by 1 over it's scaled by 1/2. So if you're talking about like a 50% changes in the local, and you have like 100 patches, so it's divided by factor of 10, so you got roughly less than 1% changes. Okay, and this is, well, I've also felt like large patchy clouds, but this gives us a new possibility to think about this program. Maybe at some brown dwarfs, we actually see a lot of patchy clouds or a lot of this temperature fluctuations that just modulated by this rotation modes, and we see these light curves, within 1%. Since Karen is looking at me, I just can show my vision size here and answer the questions.
Okay, we have questions. Trent.
Hey, G, I just want to, can you clarify that last slide that you were saying? Are you saying that you can take the Fourier transform of a long-term variability survey and distinguish between jets and no jets, or are you saying you can't distinguish them?
Sorry, I don't think our model is realistic enough to distinguish the jets and the no jets regime, because it really depends on a lot of like cloud opacity, like relative cooling scheme, things like that. So we cannot say, okay, if we observe this kind of pattern, we make sure, okay, we see the jets. No, I don't think so.
All right.
So going back to your initial plot, where you show the two parameters that define the control the formation of jets, radiative damping and internal heat flux. I see that if you start with Jupiter, we know we have jets, and we know that the internal heat flux and the relaxation, the internal heat flux is low and the relaxation time is long.
Yeah.
So and then as you go to the T dwarfs and then to the L dwarfs, obviously the energy input rate increases enormously, but the relaxation time also goes down a lot. Which effect wins out? Do you expect the warmer objects to be more have more jets or more turbulence?
This is a fantastic question. So that's why we put like two brown dwarfs here, like in two regimes, because it really depends on the specific parameter regime. In the case on a complicated processes governing what is the energy input rate there. It's not just the whole internal heat flux. It's because you should have the differential heat flux that drives the dynamics essentially.
So we can't yet be sure whether L dwarfs, for example, should have jets or not.
Well, so far it tends to be we do have some like this kind of slope is like 0.6, and if we can, I don't know if you can observe that, in from the data, what kind of slope of the real atmosphere is, so we can compare the two slopes and see if we tend to have jet patterns in the colder hemispheres. I don't know.
Okay, great. Let's thank Xi again, please. Okay, our next speaker is going to be Beth Billing.
All right. Can everyone hear me okay? Cool. So I'm going to talk about some results from a brown dwarf that probably needs no introduction for this particular crowd, but I'll introduce it anyway. This is a map of it. This is this Doppler imaging map that we've heard about already, but here are Luhman 16A and B. These two brown dwarfs are pretty much the closest brown dwarfs to the Earth. They were only discovered last year because they pretty much got lost in the confusion in the galactic plane. And because they're so incredibly close, only 2 parsecs away, they really enable a level of characterization that's impossible for any other brown dwarfs in the sky. And they are pretty much a very prototypical LT transition binary. So A is an L7.5, B is a T 0.5. This paper, the discovery paper, Luhman 2013, came out in March, and within a couple of months there were quite a few additional papers on this object. And one of the really obvious things to do here, especially in the context of some of the other work that's been presented in this session, was to look for variability. And it was found immediately. So this paper, again, discovery paper was out in March. This paper was out in April. This is the result of 12 nights of variability monitoring using TRAPPIST, a robotic telescope, in a combined I plus C filter. And it's really variable. It has a period of about 5 hours, and this is just kind of looking at a periodogram. And the other thing is, this is a very variable variable. So it changes a lot, even night by night. So I want to point out one other very interesting thing about this particular variable. I'm going to go back to this map I showed on the title page. This is the Doppler imaging map, so it's done using CRIRES at very high spectral resolution. And one result of that is there's a very good V sin I measurement for this object. And then if we make a pretty acceptable sort of assumption like, okay, it's a brown dwarf, it's about the size of Jupiter, then we can back out essentially the inclination for this object. And doing that, this object is actually, this is, at an inclination of 30 degrees or less. So unlike other variable brown dwarfs where we don't have that great an idea of what inclination we're looking at, this one really is, we really are looking about at the equator. So that's just an interesting note on that. So this was in April, and by the time this came out, we had just gotten a very interesting data set on this object using Grand. So any Lord of the Rings fans here? Yeah, so Grand is also a battering ram in the Lord of the Rings universe, but it is also a gamma ray instrument. So it is a 7-band simultaneous imager, GRIZJHK, on ESO 2.2 meter telescope, and Luhman 16A and B are pretty much the only brown dwarfs in the sky bright enough to do this kind of monitoring at a 2.2 meter telescope. So we got 2 epochs of monitoring, taken about a week apart. The first epoch was done in an unresolved mode, so basically just like a transit sort of spectroscopy observation. We just defocused everything, and these are combined light curves for both the A and the B components. This is after subtracting a combined reference star, but where you can see these little points here, that's what happens when we take other reference stars and subtract the combined reference star from the field, just to kind of illustrate the stability here and what our realistic photometric precision here. So these are simultaneous then for R, I, Z, J, H. K, we had some trouble with reference stars, so it didn't really yield a useful result in this case. And what came out of this, over these 4-hour observations, unfortunately too short to probe the entire period, was that we saw some very interesting anti-correlations. So R and I appear to be anti-correlated here in Z, J, and H. And again, this is combined, so we made the assumption that was made previously by Guillaume et al., that this was largely due to the B component, but we really wanted to test that. So in our next observation, we did resolved imaging instead. And these are the results. So again, the little dots give you the idea of what reference stars are doing. So to get these light curves in this case, we had to do PSF subtracting photometry. Aperture photometry really didn't work because they were too close together. And for the optical bands, where it was quite well resolved, we get really nice result again. We see this RI anti-correlation with Z. And we maybe see a hint of variability in A. I'll get to that later. And in the infrared, H, again, looks correlated with Z. One really weird thing we saw is that J seemed to turn off. And you can see, again, little dots give the idea of our photometric accuracy, and J really doesn't vary beyond that. And K may be somewhat anti-correlated with the rest of the bands as well. So just to summarize, what we got from that is that we saw this very persistent anti-correlation between RI and ZJH. K was about 100 degrees out of phase with H in the epoch that we got a good K observation. And in the second epoch, we didn't see any variability with J. So when we saw these phase shifts, we were very interested in comparing it to the only other known brown dwarf with phase shifts. This is results from Esther Buenzli. And she was able to show that in this case, the phase shift was correlated with different atmospheric pressures. So if you just look, these are our ground bands. This is a model spectrum and what photometric pressure we're probing. What you can see is Ri and K probe higher up in the atmosphere than Z, J, and H. And we did find that there might be a similar anticorrelation. Unfortunately, J turning off the second epoch doesn't play into this picture well. And again, Esther may talk about some results she has on the same object, which also don't show necessarily the same phase shifts. And theorists, if you have any input about what might be causing this, would love to hear about it. So one other result, we have tentative detection of variability in the A component. So again, photometric precision is given by these little dots here, and when I blow up this scale, it's maybe a few percent variable. So we now have follow-up epochs from February. Unfortunately, the photometric precision, seeing was not as good. In our first epoch, we had about 0.8 arcseconds. Seeing, second epoch, was above 1 arcsecond. So we're still working hard on the data reduction, but here is one preliminary result. So this is just Z-band. These were longer observations, so 7 hours observation. A, still working on it. I don't, initially, at least for now, this is just a single reference star, not necessarily pulling out the tentative detection of variability, but again, not the same quality of data. B is, again, quite variable. And now we do actually, again, pull out this 5-hour period. All right, I'm going to end there. And for my conclusion slide, either you get this meme or you think I'm totally crazy.
Great, thank you, Beth, for being perfectly on time. Very impressive. Let's start with Adam.
Yes, you guys didn't recover a phase.
Oh, I wasn't going to talk about that.
Okay.
So I was going to ask about your light curves for the resolved light curves. It looks like in the K-band, the A and B components are doing opposite things.
Oh, sorry. Getting back there, Beth.
Yeah, right there.
Right here. Yeah, it's worrisome. Yeah.
Yeah. Is it? How many calibration stars did you have in the field?
So we had 5 or 6 calibration stars, but the reason I ended up believing this is that we do have, so I don't think A is variable beyond our photometric precision. So we can also use A as the reference star, and that's the only reason that I would believe background variability.
Any other questions? Okay, let's thank Beth again. Great, so our next talk is going to be from Esther Buenzli.
Hi. So I apologize, my voice is a bit hoarse, so I hope I can get through this okay. So I want to speak a bit about the variability beyond the LT transition for the Metchev dwarfs, and Zhang already showed a teaser of these results, and that show very interesting features that are quite different than the LT transition objects. So beyond the LT transition, we think that the silicate and iron clouds have largely sunk below the visible photosphere. So you're left with a mostly a clear atmosphere, except maybe for some sulfide clouds that could also condense, that were shown by a paper by Carl and Morley. And we are now actually looking in very large detail at this variable brown dwarf here, 2 mass 2228. And what you can see is that this is already one of the kind of redder blue-brown dwarfs. So it's really on the red side of the Metchevs, which may indicate really that there is some of these sulfide clouds that could redden the spectrum a little bit. So we got HST time series with wide field cameras 3. On top you see kind of the maximum and minimum spectrum. You don't see much here because the variability level is quite low on this scale, but the signal to noise is very good. And if you just integrate this over the whole time series, you can see in the bottom plot that this is indeed variable on the order of about 2%. And we were very lucky to also get simultaneous Spitzer observations. And the advantage here is, first of all, you get, of course, a different wavelength, and also you don't have to deal with these gaps in the HST time series that you get because HST circles the Earth So we get also a continuous light curve from the Spitzer data. And so what we wanted to do was study the spectral variability in a bit more detail. So instead of just looking at the spectrum, we made light curves integrating over different bands, looking at the peaks and at the valleys in the different regions, and then looking what we got out of that. So here is the plot for these 5 different wavelength regions, and kind of the peak of the J and the H band, and the deep water absorption band, and an absorption band that's mainly the methane, and then the Spitzer light curve. And the first thing that we immediately noticed was that the phase of these observations was quite different. So all of them were quite sinusoidal, very similar, and the rotation period is 1.4 hours for all of them, so a very fast rotator. But the phase was really quite different. So the J and the H peak were quite similar, and then the water and the methane were sort of anti-correlated, not exactly, but more or less. And the Spitzer was the most interesting. It's kind of at an intermediate phase of about 120 degrees shifted from the J band. So, and then a second interesting thing is if you look at the amplitudes. So the largest variability we see is actually in the water band, about 5%. Then the second largest is the H band, then the J and methane, and at the end the lowest one is the Spitzer IRAC band. So I'll get back to that as well. So first, to understand a bit more about the phase shifts, we did some modeling. So this is with models from Caroline Morley 2012. With the sulfide clouds, there is no patchiness in this. It's just to model the average spectrum. But we found that we could fit the spectrum quite nicely with these sulfide clouds. Any of the clear models really didn't work to model the spectrum. And then we looked at what is the pressure level probed at these different wavelengths. And if we then plotted the phase shift versus the pressure, we saw this kind of correlation of the two. Except this one, the CH4 point, which doesn't fit, is actually the one in the model, which actually here are some missing opacities. So the model really does not give you the right pressure. So we can probably shift this point up, and it will still fit into this picture. So what is causing this phase shift? It would be quite hard to imagine just patchy clouds resulting in something like this, because you would need sort of a sheared cloud which spans half of the brown dwarf, which is probably not very realistic. And so the first theoretical effort to describe this was made by Robinson and Marley, 2014. And so what they did was they didn't look at clouds, but they actually looked what happens if you introduce a temperature perturbation deep in the atmosphere and you let it propagate up through the opacity windows. And what they found was that indeed you start to get some phase shifts. For example, the Spitzer water curve will be shifted in phase with respect to the J band. Now, so this is still a quite simple model. It doesn't include any clouds, which we do need, and it was also a bit on a longer time scale than our very fast rotator. But it shows that there's really probably these temperature perturbations that can start to explain this variability. So very recently, a few days ago, there was a new paper by Caroline Morley on the archive, which was actually looking at the effect of such hotspots on the spectra. And so she introduced hotspots at different levels in the atmosphere to see what happens to the spectrum. And what she found from the model was that you would expect this type of hotspot to give a really large variability in IRAC 3.6, which is a band we did not have in the previous observations. It also gives quite strong amplitude in the water band, which is where you see the strongest amplitude, but you would not get any variability at all, basically in JH and the 4.5 band. So it might explain the water variability, but we would still need something to explain these other bands. But this hotspot predicted the really high 3.6 micron variability, and in the STORMS program, which is led by Daniel Alpay, we got some new data on this object covering both channel 3.6 and 4.5, as well as simultaneous HST data. And indeed, what we found was that the largest variability is really given in the 3.6 micron band. And so this would agree with this hotspot model, at least for the water and the 3.6 band. The patchy clouds also have can also have an effect. So these patchy cloud models would give the strongest variability in J and H and very low in water and IRAC 4.5. So this could a combination of patchy clouds and hotspots could reproduce some of the variability, with the caveat that we see actually the H being larger variable than the J, so we would need to figure out what's going on there. At the LT transition, this is really very different. We see for all the objects we have so far that the water varies in phase and it is at lower variability. So this is 2139 and some new observations by Luhman 16 that are also presented on my poster. It's not 2228 is not the only variable mid-T dwarf. From our snapshot survey that Stan already introduced, we got a few other objects that are T5, T6 that are variable, but only in these really narrow bands. One of them in the water, another in the methane, and one in the J-band peak. So it seems to be very diverse, and none of them has this strong multi-wavelength variability that we saw for 2228. And we are getting some follow-up on these two objects with HST. So and just to mention the results from that survey to go into the variability frequency. So we had a bit smaller sample, about 22 objects, and mainly we had the Ls and the mid-Ts. We didn't have a lot of objects in the early Ts. So the red are the confident detections and the green the more tentative ones. And what we found was that on the low-level variability, we found a fraction of about 30%, or it could also be higher because our observations were very short. And we did not find significant differences between the spectral types for this low-level variability. But we did not find any of the high amplitude variables, which, as we heard from Jackie, might be concentrated in the early T dwarfs. So this is still pretty much consistent with both the two surveys that predict different things for the LT transition. So the take-home message here is that the mid-T dwarfs can show very complex spectral variability. It's quite different from the LT transition. They could result from a combination of patchy sulfide clouds and hotspots. Yeah, thank you.